Now coming to the sequence network of synchronous generator. So three phases are represented, A, B and C, and the impedances of each phase ZA, ZB, ZC, and the EMF which is developed is represented by EA, EB and EC. And we also have a neutral line whose impedance is denoted by Zn, and IN is the current which is flowing through the neutral line. And IA, IB, IC are the currents in the phases, three phases respectively. See, if you take an alternator generator, this three-phase generator, it is always designed in such a way that it produces or it generates only the positive sequence voltages. So windings will have same impedance and they are symmetrical, and the voltage developed in each phase, that is EA, AB and EC, will also have the same magnitude, but they actually differ by 120 degrees to each other. Now when the system is balanced, no current will flow through the neutral. But when the system is unbalanced, that is the sum of currents IA plus IB plus IC is not equal to 0, and the return current flows through neutral, which is given by IA. Now coming to the positive sequence network, as I have said, the generator or alternator is designed only to generate the positive sequence voltage. So that voltage I am going to represent here as EG1, and the impedance is given by ZZ1. So generally this ZZ1 is nothing but the J times XT, the direct axis reactance. But when there is a subtransient fault occurs, then instead of JXD, the generator impedance on positive sequence network is given by J times XT double dash, which is the subtransient reactance. So here it is, generator is designed to develop only the positive sequence, sorry, it is not current, it is voltages. Now coming to the negative sequence current. See, in negative sequence current also, the negative sequence current flows through all the three windings, and the voltages will be developed in the three windings. But the problem here is, see, as when the positive sequence currents are flowing, the rotor rotates in one direction. But again, when the negative sequence currents are flowing in the windings, so the rotor has to rotate in the opposite direction, which must happen simultaneously. So this cannot happen in a generator. So the negative sequence voltages cannot be considered here. Okay, and the impedance ZZ2 is nothing but the average of the quadrature and direct axis reactance. And when there is a subtransient fault current, this generator impedance in negative sequence current is given by J times XT double dash. Now coming to the zero sequence network, since there is a neutral path, the impedance here represented is 3 times Zn, and this is the ZG0. And ZG0 is nothing but J times XL, which is the leakage reactance of the winding. The neutral impedance comes into picture since there is a return path through neutral. So that is why the 3Zn term comes into picture, which is available at the neutral. Now for generators, if you observe, for ZZ1 it is J times XT dash, and ZZ2 J times XT double dash, which are equal. So that's why ZG1 equal to ZG2, and this is much greater, or this ZG1 and Z2 is greater than ZZ naught. So the typical values of positive and negative sequence impedances range from 12% to 14%, or 0.12 to 0.14 per unit, and the zero sequence impedance ranges from 5% to 7%, that is 0.05 per unit to 0.07 per unit. So you make use of this about the sequence networks of alternator. So as we know that in any power system you are going to come across this transformer, generator and transmission lines. So representing these three in terms of sequence networks is important. So we have converted that into the sequence networks, positive sequence, negative sequence and zero sequence network.